So today it's only going to be problems. I'm going to start with easy problem and one challenging problem at the end. So these problems here come from that website here, and it's typical AP physics problems which are similar to MCAT problems. So it's mostly conceptual questions. So first one, very easy. You have a spring attached to a mass and it oscillates back and forth. So it's a simple harmonic oscillator. The period is given and they are asking to find the frequency. So it's just definition. Frequency is half, not half, but 1 over the period. So it's a reciprocal, and 1 over the period is 1 over 2, which is 0.5 hertz. So that means in 1 second, you have half of a cycle. It makes sense. If you have 2 seconds for 1 cycle, so in 1 second, you're going to have half of a cycle. Okay, so very easy. Number 2. So again, that's the same one, same period. So it's pulled to the right and then you let go. So if you let go from the right to the left, to the leftmost point, so that means that will be half of a cycle, right? Because you go from amplitude A here to amplitude minus A. So half of a cycle will be 1 second. So the answer is A. So here they talk about earthquake. So you have vertical oscillations up and down and up and down. And you have the frequency. And so it's the same question. So you go from the highest point to the lowest point. So highest point to lowest point, that will be half of a cycle. If you go from highest to lowest back to highest, that will be 1 full cycle. So this is half of a cycle. So the period is that 1 over this number, and you get 6.6666 seconds. So that will be for 1 cycle. So half a cycle will be 3.3 seconds. Okay, so that's also easy. And then here they talk about the amplitude doubled. So it means you have the same oscillator, but you're going to pull the mass farther away, right? So you increase the amplitude. So is it going to change the period? And the answer is no, because the period for a spring is only depends on the mass and the spring constant. Here you see no amplitude. So that's only, so there is no amplitude here. So that means the answer is, so it stays the same, so the answer is C. So here you have 2 identical blocks, so the mass is the same, but they are attached to different springs. Which one has a larger spring constant? So remember that the period depends on K. So if K increases, the period decreases, so the frequency increases. It makes sense if you have a very stiff spring, and I think I showed you that last time. If you increase for the same mass, you see here it's oscillating back and forth. But if you increase, so you can look at how long it takes for 1 cycle. If you increase the spring constant, you see the frequency is going to increase because you have more recoil. Okay, so the restoring force will be larger. And then of course, if you take a spring which is more flexible, it's gonna take more time to do one cycle, so the frequency will be smaller. So the answer is the one with the largest spring constant will be the one with the largest frequency. So that must be the red one, because you see how squeezed it is relative to the blue one. So the amplitude does not matter. But if you look at the cycle, you see, you start from here, that will be the period, the time for one cycle. So you start from the equilibrium position, you go up, back to equilibrium, you go down, back to the same place. You compare that to the blue. So it starts before and it ends after. So the period for the blue is larger, so the frequency will be smaller. So the one with the largest frequency has the largest spring constant. So the largest spring constant is the red spring. So here, so you have two identical blocks. Oh, you increase the mass. You increase the mass here for the same spring. What's going to happen to the period? So you are multiplying, so you multiply the mass by 2. Okay, so you multiply the mass by 2. So multiply the mass by 2. Okay, so you see here the mass is multiplied by 2. So the new period will be 2 pi, and here the mass is multiplied by 2. So if you compare this one to that one, that means the new period will be larger, and it's multiplied by square root of 2. And square root of 2 is about 1.44. So it increases by a factor of 1.44. We discussed those type of problem before, right? So 1.44 times 2, 1.44 times 2, of course, you're going to get 288. So it's going to be about that answer here. So this one is interesting here because we discussed that previously. So you have here the displacement. So it's very much like this slide here. So you have the displacement, and they want to know what's going on at that point here, when it reached that point here. So they want to know about the spring. No, they want to know about the velocity of the mass and the restoring force. So that point here, you see, it's a negative A. So the amplitude, the position is at x equals minus A. So it means if you have a spring, let's say this is positive, that's your x, right? And you have an oscillator, so that will be the equilibrium, the position here. And the oscillator can be squeezed here, or it could be here, or it could be all stretched out here. So that position here is A, that position here is minus A, that position here is 0. So at that position here, you see that x equals minus A, okay? And if you look at the period, not the period, so if you look at the slope, of course, you see that the x component here, the x component equals 0. Okay, so you know that because when it reached that position here, it's not moving anymore. So it went from negative velocity to positive velocity. So it means that it was negative. So it was just going this way in that direction. That will be the motion, and then it reverse, and then it's about to go in this direction. So it's on its way to reverse the motion. So where is the restoring force? Restoring force is going to be in this direction. So we have that the position is negative A, the velocity is 0, and the restoring force is positive. So I know which answer is that. So Vx equals 0, and the force is positive. So it must be this answer D. Now, if you go back to the slide here, you see that at that position here, displacement, the velocity is 0, so it's not moving. Okay, at that position here, it's not moving. And you see that the acceleration here is maximum, and the acceleration is positive. So it means the force is also positive. Okay, so that's interesting. So which one? Now we are here. So let's look at this position. So at that position here, you see that x equals 0. So it means it's going through its equilibrium position. So you have 0 here, you have a minus a. So it's there. So I don't know if it's going this way or it's going that way. So let's look again. So you see here the slope is, let's look at the slope. The slope is negative here, and the slope is negative here. So it means it's going in this direction here. So the x component of the velocity is negative, okay? Because you see it's moving offshooting the equilibrium and moving to the left. So the x component of the velocity is negative here, so it's negative. And what about the force? The force has to be equals to 0 because the spring is not stretched. So we want to have well, here the x component is negative and the force is 0. So the answer would be C. And if you go back to here, you see that we have could be here or it could be there. So here the position is negative. The position here is here, and the slope is negative. So I am at that position here, which means the velocity here is 0, is maximum and negative, and the force equals 0. So I am at that point here. Okay. So what did we say? I think we answered right. The velocity is negative and the force is 0. Okay. Oscillate when the block is at the lowest, you see that the acceleration at that lowest point, the acceleration will be pointing to up. So the acceleration is positive, right? So if you go back to here, let's look at the acceleration. The acceleration is maximum pointing up. Okay? Then the acceleration is 0, and then acceleration is pointing down. The velocity is 0 here, Okay, we already discussed that. So the pendulum, we already discussed that. That's a tricky question, typical question. If you double the mass, you want to say, okay, if you double the mass, maybe it's going to go faster. But actually, when you look at the equation for a pendulum, for the period, so you have the period equals 2 pi. It's an approximation. If you're not moving the pendulum too far away from its initial position, it's going to be square root of, and then you have L over G. So here you have no mass because of Galileo, right? It means that regardless of the mass, the object in free fall, so we neglect friction, will have all the same acceleration. So the mass does not matter. So it will keep the same period. And all that we already did together. And here, for example, if you have all those pendulum, they try to trick you because, for example, this one has more mass, this one has less mass. But what matters here is the length. If it's on the same planet, it's just the length, okay? The period depends on the length. The shorter length will have the smaller period, so the higher frequency. So lowest frequency will be the one with the largest length. Okay, so those are easy problem. So let's try to do one more challenging, but it's a typical one. So if you can skip it. Typical one. So you have the Earth, and there's a tunnel, and there, we put a mass inside the tunnel here at the very top here. What's going to happen to the mass? Is it going to go through, or is it going to be staying in mid-air, or maybe it's going to be stuck here? We neglect friction. What's going to happen to it? Okay, so the first thing for that is to review the math. And let's take, for example, let's start with taking two disks. So this one has a radius 1 and like a disk, right? Made of the same material R2. So it's in 2 dimensions. So of course the area 1 equals pi R1 squared. When you are finding the area, you always have a square somewhere, the size squared, and the area here is pi R2 squared. So I can write the following. I can say the area 2 is to the area 1 what R2 squared is to R1 squared. And it's flat. Now let's say I have a sphere now, right? So a sphere with a radius R1. Okay, so the volume is 4 pi R cubed. So that will be the volume 1. And I have another sphere. No, I can make it smaller if I want, doesn't matter. R2. So of course the volume 2 is 4 pi R2 cubed, that's R1. So you can say the following. You can say that the volume 2 is to the volume 1 what R2 cube is to R1 cube. So there is a cube dependence here. Okay, now, and they are made from the same material. Actually, it doesn't matter here if it's not made from the same material, but let's say they are made from the same material. And what's going to happen to the mass if they are made from the same material? So you know that the density, which is the same here and the same there, is mass over volume, right? So for the same density, you see that the mass is the density times the volume. So if I want to compare the mass 2 to the mass 1, I can say that mass 2 is to mass 1 what volume 2 is to volume 1, which is what R2 cube is to R1 cube. I hope you see that, right? Because if you have a mass 2 here, volume 2, and they are made from the same material, I have volume 1. If I take the ratio, so M2 over M1, you're going to say it's the same as volume 2 over volume 1. Okay, so if those discs, for example, are made from the same material, so I can say the mass 2 over the mass 1 equals R2 squared over R1 squared. But we're going to work in a 3-dimension. Okay, so that's one thing. So let's take a sphere. I don't know if I have a sphere here. So this is a sphere and this is the Earth. And to a first approximation, I'm going to suppose that the density of the Earth is everywhere the same. It's just an approximation. And you have the radius r. That's the radius r. And if you are on the Earth, so this is you have a mass m, you're going to be, everything happens like all the mass of the Earth is at the center here, and you are attracted by the Earth. And the force here is called the weight, and it's pointing to the center of the Earth. Right? So that's physics 1. So your weight or the force here will be a constant G times your mass times the mass of the Earth times the radius square of the Earth. Now, if instead you cut out a sphere here inside the Earth, so I don't know. No, can I do that? Okay, so now I'm located here for some reason. Let's say I have a tunnel. There is no top and bottom, right? So it doesn't matter how I make my tunnel. Have a tunnel here. Oh, this is fun. So that's supposed to be a tunnel. So that's a tunnel here. And now I'm located inside. I'm here. Inside the tunnel. Let's say I'm here. Just for the computation, I'm going to be here. And that's a sphere here cut out inside the Earth. Right? So let's consider here, and the tunnel is going through here. So this sphere is not physical, but the tunnel is. So what we have the Earth and the tunnel. That's all we have. But here I'm located at a distance r. So that's a distance r. So physics says that the force acting on you will be only due to that sphere here. Okay, it's not going to have any influence from the mass here. You're going to be influenced only by that sphere here, and everything happens like all the mass is at the center. So you're gonna have a smaller force pulling you toward the center. So the question is, what's going to be that force here at that distance r? So F at that distance r will be G. So you have the same mass. Now it depends on the mass of that cut out sphere here. So that's going to be the mass inside over r squared. But that mass inside has a volume that depends on r, right? So we say that the mass inside, if you want, will be the density of the Earth, which is the same everywhere, times its volume. So 4/3 pi r cubed. And the mass of the Earth is, like we did before, pi r cubed. So I can see there is a ratio between them. So I can say that mass inside, so the mass that is pulling me toward the center over the mass of the Earth is just r cubed over the Earth radius. So the mass of the Earth, the radius of the Earth, and g are just constant, right? Okay, so now I'm gonna write this. So the force acting on me at that distance lower r equals g times the mass times, I'm gonna use this here. So it's gonna be the mass inside, so that will be r cubed over here. And then I have an r squared here times the mass of the Earth. So you can simplify, so cross this out. So the force acting on me at a distance small r from the center of the Earth equals g, my mass, the mass of the Earth, and that's a constant here, r, is it supposed to be r cubed, and then r. Okay, I hope this is correct. Yes. And look at that. This is a constant here, so it's a constant. So you see that force here acting on the mass is proportional to r. It's proportional to r. So this is very much like F equals kx. It's a restoring force. And each time a force is proportional to the displacement, so from here to there, that will be your displacement. That small r is your displacement. Then I expect a simple harmonic oscillator. So it means when you are here, you see the force acting on you, it's going to be larger. And then here, it's going to be 0 because r equals 0. And then I overshoot here because of inertia. And now it's going to be in the opposite direction. Here it's going to be there. And here it's going to be maximum. Okay? So you're going to oscillate back and forth. It doesn't matter where is your tunnel. There is no top and no bottom. So it's a simple harmonic motion. So now we know how to find the period because we know that F equals ma. So I have g, that's my mass, the mass of the Earth, over r cubed mass, and it's a negative here because if positive r is in this direction, the force is always in the opposite direction, equals ma. So cross this out, and you have an r here. So then you have acceleration plus G. No, I have it twice. So G, the mass of the Earth, the radius Q, and then you have R equals 0. Or you can say that R dot dot, if it's a acceleration along the R, so it's like X if you want. You can replace it by X. And have a R. So you can replace that by X. I have everywhere, but you can say, okay, that's going to be X dot dot. So that will be the acceleration plus G, the mass of the Earth, R cubed, R equals 0. Oh, it's X now. So we can say this is X. So we have discussed that already. So that here, that's going to be your omega square. So that's going to be the angular frequency. Okay? And then physics stops here and then math takes over. So you just have to take your calculator. So here we have that omega sub 0 equals G times the mass of the Earth, and that's the radius of the Earth, and you have a square root. Okay, and this is equals to 2 pi times over the period. That's the angular frequency. Unit is rad per second. So we have that the period equals 2 pi, and then you have the square root of radius cubed over G times the mass of the Earth. Okay, so the radius of the Earth is about 6,400 kilometers. So you multiply by 1,000 to have meters. The mass of the Earth is 6 times 10 to the 24 kilogram. And then you have G. It's the universal constant is 6.67 times 10 to the negative 11, whatever units that is. Okay, so you have to plug that into here. You want to multiply here by 1,000 to convert, and then you get the units in second. And when you do when you convert to minutes, you have to do it yourself. When you convert to minutes, you get about 84 minutes. Okay, so multiply this by 1,000, convert to meters, then you raise to the third power, enter, you divide by this number, enter, divide by this number, enter, take the square root, enter, multiply by 2 pi, you get 84 minutes. So that's super interesting because 84 minutes is the time it takes to go around the Earth in a circular orbit. So the lowest orbit possible, very close to the surface, will take 84 minutes. So is that surprising? You go back and forth and it takes 84 minutes, and you go around, it takes 84 minutes. And actually, that's what we discussed together, because if you go back to the simulation, this one here, for example, you see the time it takes for a satellite to go around the Earth is 84 minutes. It will be the same time that it takes if you fall in a tunnel inside the Earth to go back to the surface of the Earth. So it's a nice way to see how math is serving physics, right? Okay, so next I will talk about resonance. Stop that.